Okay, in this video, we're going to talk about how you actually go about finding limits. If you see like limit of this as x approaches that, then how do you actually figure this out? So first of all, we're not dealing with infinite values. We're going to just deal with the limit as x approaches a of some function where a is not equal to plus or minus infinity. There's another video on the case where it is plus or minus infinity. And just a reminder, in case infinity does pop up somewhere, there's some basic some basic ideas of infinite arithmetic. It's not formally correct, but intuitively, when you're dividing something finite by 0, not 0, but something like 1, then it's kind of like plus or minus infinity. As the denominator gets big, the overall thing gets small, and vice versa. If you're dividing by infinity, a finite number, then that's like it's going to shrink down to 0. You're making the denominator very large. And then other things like infinity plus infinity, infinity times infinity. Obviously, as these things are getting bigger, then these other things should get bigger too. I mean, infinity plus infinity should equal infinity and so on. So with that in mind, step 1 when finding a limit is you plug in the value. And there are 4 possibilities of what can happen. One is that you just get a finite number. And in that case, I mean, you're done. This is what we call the continuous case. We say that the point in question is a point of continuity of the function. So easy example, limit as x approaches 3 of x squared plus 2. You would just plug in a 3 and you'd say, well, 3 squared plus 2 is 9 plus 2, which is 11. So that's just a regular run-of-the-mill finite number. So that's check. I mean, it's continuous in this case. It means that if we draw the graph of x squared plus 2, as we approach the number 3 on the x-axis, the limit exists, and it just equals the value of the function at that point. So it's a nice point of continuity. This is really the nicest, easiest situation, and because of that, there's not really a trick there. It's the one you're also kind of least likely to see in practice. But if you see it, I mean, don't look a gift horse in the mouth. It's as nice as that. So another thing that can happen is you come to plug in the value. When I say plug in the value, of course, we mean plug in this a here. Just plug it right into the definition of the function. So that's what we did here. We plugged in 3 into x squared plus 2. Well, what you might have is, the function might be defined in a piecewise way. It will be like f of x equals, 3x squared for x bigger than or equal to 1, and then for x less than 1, it's like negative x or something. I don't know. Some piecewise defined function, and usually they're going to ask you about the limit of this function as it approaches that horrible value where things change in definition, these shifts, like 1. So that kind of deserves a video all on its own, and we've seen examples of this in the quizzes. But you can't just plug in the value directly. In this case, it just doesn't even make any sense. So what you have to do is you have to find the junctures first. So in other words, where does the definition change? Right, here it just changes at 1. So 1 is what I'd call the juncture. If I had, for x less than 1, but also bigger than 0, it's negative x, and then I'll extend the definition, it's, x cubed when x is it's less than or equal to 0. In that case, then there would be 2 junctures. There's a shift in the definition at 1, but there's also a shift in the definition at 0, so 0 would be another juncture. So I'm just giving you this horrible example just to explain what I mean by juncture. I think it's pretty straightforward. You have a piecewise defined function. What are the separate pieces and where do they shift? Where does the shift occur? That's what I mean by a juncture. So then what you have to do for these junctures, every time you end up with a piecewise function, is you check the left and the right hand limits separately and say, are they equal to one another? Right? So for the limit to exist, I erased it by now, but the limit of that function f as x approaches, say, 0 or 1, in order to figure out whether this even exists, I'd have to check the right-hand case and the left-hand case. And let's see if my memory is good. I think when we're to the right of 1, the formula was 3x squared. So if you plug in a 1 into 3x squared, you just get 3 times 1 squared, which is 3. And coming to the left of 1, well, as we approach 1, remember that there was a shift at 0. There was also a shift at 1. Here it's like 3x squared, so it's going to look like this. And that was I don't remember if it was equality or not. I think it was equality. And then it was equal to just x between 0 and 1. Is that right? Negative x? I don't remember. I'm gonna say it was just x. In which case it would look something like this. And then for x less than 0, it doesn't really matter because we're only interested in what's happening around 1. And I also forgot what that formula was at the very end. In any case, what you would say is, alright, as I'm approaching 1 coming in from the right, it looks like 3x squared, so the limit looks like it wants to equal 3. As I'm approaching it from the left, it looks just like the function x. So you plug in a 1 into x, and it looks like it's going to approach the number 1. And indeed, this function, you pick x values closer and closer, look at the corresponding y values, they're going to approach this value 1 coming from the left, this value 3 coming from the right. They disagree, so in that case, since they're not equal to each other, the limit wouldn't exist. That's always the kind of thing you're going to be asked to do with piecewise functions. So you do just want to kind of plug in the value, but you have to figure it out. Plug in the value into which formula, because for a piecewise defined function, there are different formulas, and you have to check both formulas at every juncture, coming in from the left and coming in from the right. And if you have a picture, it really does make things a lot easier. So a good idea here is to draw pictures of what this function looks like. And there's a little pro tip here. Anything involving absolute value, implicitly, it's secretly piecewise, right? Because the absolute value of x minus 7, for example, if that shows up anywhere in your formula at all, then notice that when x is bigger than 7, for x bigger than 7, that's just x minus 7. Fair enough. If x is bigger than 7, x minus 7 is going to be a positive number. So, you know, the absolute value of a positive number is just itself. On the other hand, if x is less than 7, and I really should make one of these or equal to, it doesn't matter which. But in that case, it's not just x minus 7, because now if x is less than 7, x minus 7 is going to be negative. And when you're taking the absolute value of a negative number, like negative 5, what do you do to it? You multiply it by negative 1. Multiplying a negative number by a negative number cancels the negative, makes it positive. So if x is less than 7, x minus 7, what I've written here, is negative. Put a minus sign, we make it positive. So it's given by this formula, and you should expand it as if it's a piecewise function. So this is definitely something we've seen on quizzes before. So I won't go on in that because you can watch those other videos. Alright, so let's just review. You take a formula. You see a formula, you're asked to find a limit, you plug in a value, and it just works out perfectly. It just gives you some finite number. Okay, great, it's continuous at that point. The limit as x approaches a of f of x is just f of a, and it all works out splendidly. Or what could happen is, you look at the formula of the function, and it's a piecewise defined function. And remember that even if it doesn't look like a piecewise defined function, if it involves absolute values, it is a piecewise, and you need to write it as such. The juncture is whatever's inside the absolute value sign goes to 0. There's other possibilities too. Maybe you don't get a finite number. Maybe it's not piecewise. It is a formula, but unfortunately you don't just get some pretty finite number. You get something other than 0 divided by 0. And it's important that that numerator not be 0. We'll talk about what happens when the numerator is 0 in just a moment. But for now, if you get something like 1 divided by 0 when you actually plug in the formula, like you're just taking the limit of, 3x plus 2, x is approaching 0, over x squared plus x or something. Well, if you actually plug in the value, that's 3 times 0 plus 2 is just 2 over 0. That's the kind of thing we're talking about. What happens when the limit is x? What happens when the limit, you plug in the value into the formula, and you get something finite, not 0, divided by 0? Okay? Well, what that means, and this is always what happens, let's be very clear. If you get something not 0 divided by 0, it means that in the graph of the function, at that point, there is a vertical asymptote guaranteed. Okay? So now what kind of things can happen with a vertical asymptote? Well, the 3 examples to have in mind are 1 over x squared, and negative 1 over x squared. I like these examples a lot because they model the 3 different kinds of behaviors that you can expect when you have a vertical asymptote like this. Again, the numerator can't be 0, but the denominator is 0. If that happens, it's either going to look like this. 1 over x, coming from the right, it approaches infinity. That's what these vertical asymptotes mean. Something is always going to positive or negative infinity. Coming from the left, it's negative infinity. For 1 over x squared, they're both going to positive infinity. And for negative 1 over x squared, they're both going to negative infinity. So here's the basic lesson here. If you get something, not 0, divided by 0 when you plug in values, you have a vertical asymptote in the graph, and that means that the limits, the left and right hand limits separately, might equal plus or minus infinity. It is your job to go to left and right separately and figure out, are they going to infinity or negative infinity? And you're just checking, do they take on positive values or negative values? So you can say as x is approaching 0 here, for example, if I'm coming from the right, this is taking positive values. 1 divided by x for x positive is positive. But if I'm coming from the left of 0, well, that means that x is negative. Right? To the left of 0, x would be negative. And 1 divided by a negative number is negative. So you see, it's negative to the left, but it's positive to the right. So since there's an asymptote here, the right side limit, the right-handed limit, should be going to positive infinity, whereas the left-hand limit should be going to negative infinity. What you'll find for this function 1 over x squared is that if when you square any number other than 0, you're going to get something positive, even if x started out negative. So whether we're on the left or on the right, whether x is negative or positive, x squared is always positive. So 1 over x squared is always positive. So this is positive on both sides of the limit. So for the left and the right-hand limit as we approach our asymptote is infinity. Here, same thing applies, except that minus sign out front forces everything to be negative on both sides. So that's always going to be the behavior. Either it's a vertical asymptote, and either they're both going to go to positive infinity, or they're both going to go to negative infinity, or one of them is going to go to positive infinity, maybe the right, while the other goes to negative infinity, maybe the left, or vice versa. It could go either way. So really there's only kind of three possible behaviors. Both going to positive, both going to negative infinity, or they're doing a flippity-flop, where they disagree. Okay, so that handles that. So these are the 3 options that we've discussed so far. Either the function was piecewise, in which case you find where the junctures are, usually that's where they're asking you about the limit, and you just check the left and right-handed limits separately using the separate formulas that are given. And if you can, always draw a picture there. It's very helpful. Or you just plugged it in, you got a finite number, you're done. It's a point of continuity. Or you've gotten something that isn't 0 in the numerator, but you've gotten 0 in the denominator this time. In that case, you have a vertical asymptote. It's going to positive or negative infinity, but it might disagree coming from the left or right, so you have to check it. And in order to check it, you have to apply the kind of reasoning I just did right here. When I'm to the left, am I positive or negative? And when to the right, am I positive or negative? That kind of reasoning. All right, finally, the most interesting case, and the one that's very likely to come up, is the case of an indeterminate form. What happens when both the numerator and the denominator are 0? Or what happens when they're both infinity? Or what happens if you end up with infinity minus infinity? Or 0 times infinity? And, this kind of makes sense. 0 times infinity. If we write infinity as 1 over 0, right? Then that's like 0 times 1 over 0. That's like 0 over 0. This is all, of course, not formally correct mathematics, but it communicates that 0 times infinity is kind of the same thing as 0 over 0. Or you could have called 0 1 over infinity times infinity, and it's also infinity over infinity or something like this. But the point is that if you plug in the value and you end up with any of these forms, okay, then then what do? Well, you're toast, actually. You can't say there's a vertical asymptote there because there may not be. So it could go off to infinity, it could go off to negative infinity, it may not exist left and right-handed limits, or it could equal some pretty finite value. Really anything goes. That's why it's called indeterminate. We have no idea. I actually don't think this is the correct spelling of indeterminate? I think it's indeterminate. I don't know, something you can check. Anyway, so what do you do here? It could go anywhere. You have no idea what to do. So what you do is you manipulate it algebraically so that you turn it into one of the previous types we've seen. Now, no amount of algebraic manipulation is going to take something that isn't piecewise already and turn it into something piecewise, which was case B above. So when I say turn it into something that we've dealt with previously, it's either going to be A or C. You're either going to get just a finite pretty number after some algebraic simplification, or you're going to get something not 0 divided by 0, in which case a vertical asymptote plus or minus infinity. I've said it a million times by now. Alright, so how do you actually manipulate it algebraically? Well, there are a handful of tricks that are worth remembering. So there's factor. When in doubt, factor out. You should always factor. If you have any polynomial, you should always factor. Or if you have separate fractions, then you should find common denominators. Combine them into a single fraction. That's usually very helpful. And then finally, you can multiply by conjugates. And excuse me. This is where you have something of the form a plus the square root. Ooh, that's not what a square root looks like. A plus the square root of b divided by something else. And you don't like the fact that there's a square root there. It's hard. It's making the algebra hard for you. So you multiply by a minus the square root of b. And you have to do it on top and bottom so that you're not changing anything. A minus square root of b. And on top, what's going to happen is that's going to give you a squared, if you just FOIL it out, minus b squared over c times that horrible thing, a minus radical b. And hopefully this is easier to work with. So it kind of hardly rates mention, but we did see 2 examples on the first midterm that required this kind of technique. So it's worth mentioning. But for the most part, you want to focus on these first 2 techniques. Factor things, and if they're separate fractions, find common denominators. So let's see this in practice. Let's see an actual example of what's going on here. So our first problem is the limit, erase some of this, the limit, and I'm also going to switch over to blue. As x goes to 0 of 1 over x squared plus 1 over x to the 4th over 1 over x to the 6th plus 1 over x to the 8th. So if you actually plug in 0, you're going to get 1 over 0 plus 1 over 0. Well, that's infinity plus infinity over infinity plus infinity. That's kind of like infinity over infinity. All right, so we're in an indeterminate form. So plugging in values doesn't work. We need to do an algebraic simplification. So we see separate fractions in the numerator. So let's add them together. Let's find a common denominator. So I think x squared is the same as x squared over x to the 4th, right? These cancel 2 of those. 1 over x squared is equal to this. Plus 1 over x to the 4th. And while we're at it, we have the same thing going on here in the denominator. 1 over x to the 6th is just x squared over x to the 8th. Plus 1 over x to the 8th. Right? So 2 of these guys cancel 2 of them down there and so on. So I think that all works out. So that's x squared plus 1 over x to the 4th divided by x squared plus 1 over x to the 8th. Alright, so the denominator of the denominator comes out to the numerator, the denominator of the numerator becomes the denominator, and so on. So this is going to look like x squared plus 1 over x squared plus 1. The x squared plus 1s are going to cancel, you notice, these guys cancel. And you're just going to have x to the 8 over x to the 4, which is just x to the 4th. Alright, so all we did is we combined it. It looked complicated at first, but it's equivalent. This simple algebraic, this simple polynomial here, this simple power of x. But I do want to be very clear about something. This function, the original function we're asked, if we call that f of 0 itself does not exist. You cannot plug 0 into this formula. So this manipulation was all done under the presumption that x isn't 0. Otherwise, it wouldn't have made sense from the very beginning. So what we're saying is f of 0 doesn't exist, but f of x is just x to the 4th for x not equal to 0. So I can already, if I like, draw a graph of this. X to the 4th looks kind of like a flattened parabola. That's not a terribly good drawing. In any case, there's a hole at 0. Instead of actually being equal to 0 there's a hole there. And then it's kind of the rest of it's quartic, like this. So that's what the graph looks like. So the function value doesn't exist, but the limit does exist, because everywhere other than 0, it looks like x to the 4th. So now you just plug in 0 into this formula x to the 4th. And 0 to the 4th is 0, and obviously from this picture, this limit is equal to 0. So the limit is 0. And that's how you would handle that. So notice that we started with a type D problem. It was an indeterminate form, but with a little bit of algebraic manipulation, we found common denominators. It simplified to something very simple. X to the 4th was type A. Type A means it was continuous. The function itself is continuous. The original function is not, just because, remember, f of 0 doesn't exist. But this thing that we transformed it into was type A. You plugged it in. It gave you a simple answer, 0. Everything worked out splendidly. All right, let's switch over to green. And let's do this other problem. The limit as x goes to 0 of 1 over x minus 1 over x squared. Well, now there's two problems here that kind of present themselves. The first is, I kind of want to plug in 0 into each of these cases. And if I plug in 0, this 1 over x squared is going to turn to infinity. So it's going to be something minus infinity. But what about this 1 over x term? As x goes to 0, again, what does 1 over x look like? Well, it depends. Am I coming from the right? Because if I'm coming from the right, this would be infinity. But if I'm coming from the left, 1 over x is negative infinity. So the moral of the story is, I should probably break this up right now from the get-go into two separate problems, the left and right hand limits separately, and check what happens in each case. So we'll consider the limit as x approaches 0 coming in from the right of 1 over x minus 1 over x squared, and the limit as x approaches 0 coming in from the left of 1 over x minus 1 over x squared. So the reason I decided to break up one more time, just repetition is good, is because I was going to plug in the value, and I was going to use the fact that 1 over 0 is infinity, but then I realized, hey, wait a minute, back to the front of the video, 1 over 0 is not just infinity, it could also end up being a minus infinity, and it could depend on whether you're coming in from the left and right. So it's that observation that I didn't know if I should put a plus or minus infinity there, and then when I thought about it, it actually depends on whether I'm coming from the right or left. That's the reason that I decided to break it up at this stage. But now that we've broken it up, we can actually plug in the values. Coming from the right, 1 over x, 1 over 0 looks like infinity. So that's infinity minus infinity. On the other hand, coming in from the left, it looks like negative infinity. It's like negative infinity minus infinity. Okay, so negative infinity minus infinity, if you have something that's highly negative and you subtract a large number, then that's just negative infinity. Right, so this is not an indeterminate form. But here you have infinity minus infinity, that's indeterminate. Right, because it means, I have to know, this is growing, and this is growing, and it depends, is this growing faster than this one, or vice versa? Because that's going to determine what exactly happens to it. So that's why that's an indeterminate form, and this one isn't. So negative infinity minus infinity is just negative infinity. But infinity minus infinity is the thing to worry about. Alright, so that means that if I'm approaching 0 coming in from the left, this is going to have a negative infinite asymptote. Okay? And if we're coming from the... yeah, that's true. At 0. Now, if we're coming from the right, how do we handle this? It's an indeterminate form. Well, again, I see two separate fractions. Let's combine them. Let's find a common denominator. So I guess 1 over x is the same as x over x squared. And if you subtract 1 over x squared, that's just x minus 1 divided by x squared. Now, what happens if we plug in 0 into this? Okay, if you plug 0 into this formula, what are you going to get? So why 0? Because remember, we're taking the limit of this guy as x approaches 0 from the right. So you plug in a 0, you're going to get negative 1 on top, and you're going to get 0 on the bottom. That's something not 0 divided by 0. So we've just converted this problem by a simple algebraic manipulation, finding common denominators, into a type, sorry, not a type B, that was piecewise, into a type C type problem. It's negative 1 over 0. That means that it's going to either be plus or minus infinity. So let's figure it out. Is it going to be plus or minus infinity? When x is to the right of 0, it's positive. Okay? So it's positive, but it's very small. So it's like 0.1 or something like this. So for some small number of x, some small value of x, let's say 0.1, 0.1 minus 1 is equal to like negative 0.9, right? And on bottom we have x squared, which is 0.01 in this case. So it doesn't matter. Notice that we got a negative value. Negative 0.9 over 0.01. Okay? So I guess the moral of the story, now that I gave you that specific example, here's the way you should really think about it. As we approach 0, coming in from the right, x minus 1 is a negative number. Because eventually, as we allow x to approach 0, let me actually draw it out. There's 0, there's 1. As we pick values of x closer and closer to 0 coming in from the right, eventually we cross past 1. And as soon as we're crossed past 1, for all of these values less than 1, x minus 1 is a negative number. So that's going to be a negative number. And since you have an x squared on the bottom, I don't care what that is, that's always positive. So a negative divided by a positive is negative. So it's taking on negative values as we approach 0. So again, it matters that we say that as we approach 0. I'm not saying x minus 1 is always going to be negative. I'm saying as we approach 0, eventually we cross past 1 and it becomes negative. And then we have 0 on the bottom, so this is going to be negative infinity. We're taking on larger and larger negative values, and that's the answer. So what's happening is it approaches negative infinity coming from the right, and coming from the left for an even easier reason, it approaches negative infinity. It just worked out well there. So how does the picture look? Not only is it approaching a negative infinite asymptote from the left, it's also going to negative infinity coming from the right too.